Good afternoon, and we welcome you in the afternoon session of ninth day. So it's basically my last session and second last session of our FDP. So before starting with it, if you have any questions, anything from the last presentation on the facial expression. Okay, so we start with, so then this session, and what I'm going to cover, here again, as we emphasize that medical image is basically that highest level of application of the image processing, where your accuracy and your precision um, matters at the finest degree. So before coming to this part, when we are basically going towards the MRI, so in this case, when we see it, so basically, what is the need of this? What type of problems are there? See, the first fundamental thing what we need to understand that this brain, etc. Brain, etc. is such a organ that which is very complex one. It is very complex and we say complex in structure. So it can't be opened. So even whenever we have to analyze anything, whenever we have to diagnose anything, so imaging becomes the key step to find out any problem or to understand the any issue in that part. So in this case, so for example, the things can be diseases can be divided into the four parts. The first, basically, it is the neoplastic disease. It is abnormal. Yesterday lecture going to provide completed something left. I think that has been that has been completed. She has delivered it. So, had you any question? Oh. So see, regarding it, so when we are saying neoplastic disease, so it basically contains the abnormal and uncontrolled growth of cells. So two types of basically tumors are there, benign tumors are there, definitely. These are tumors which need to be removed out, but they are not that dangerous. Malignant tumors that are really a very problematic thing. If they are not removed out timely, it may lead to the death of the person also. So what we can see that this is basically a image plane. Now you see how much difficult it is to interpret this image. Unlike the other image, other part. Why? Because it is basically the cross-sectional. When you are seeing this part, it is basically the cross-sectional. Cerebrovascular disease. So what is this? Here it is basically what you are seeing. It is affect the blood vessels and blood supply to the brain. What type of problems come? Basically the stroke, transient, ischemic attack, aneurysm, etc. Degenerative disease. Here, what we see basically that it is the in degenerative, it is the most we say dangerous. Why? Because it leads to deterioration of tissues, organs, or functions over time. You know in which disease these type of problems occur, where you begins to forget the things, where you begins to forget the things not temporarily but at a permanent level. So Alzheimer disease is there, Parkinson's disease is there, Huntington disease is there, multiple sclerosis disease is there, neurodevelopment disorder. Since this basically it affects the development of the brain and the nervous system. Here autism spectrum disorder is there. So what we are saying, so this is again what you are seeing. Are you seeing this colored image? Are you finding it bit different from the another one? This is a bit colored one. Can somebody maybe first see why is it so? Because if you see this image, see what is this one? This is basically the PET. This is the PET scan. Positron emission tomography. So that's why the colored one here. So when we see about the statistical cases of neurological disease in worldwide and in India, that you can realize that it is for the, if you see the new cases, see it is every year, if you really take, it is basically 12.2 million. So can you imagine, see, it's basically around 1 crore. It is 1.2 million. So such a cases, see, in India, you can see brain stroke is that much prevalent. And you see, and among these 12 lakh, around there are 8 lakh are the death cases. Brain tumor. Brain tumor, see, again, see, in India, the new cases is 28,000 and death cases are 24,000. And especially in basically the rural segment, etc., it is very difficult to find out. People are not aware. So they are actually these death cases, etc., are very more in number. Alzheimer, you can see it's around in world. It's basically 55 million. In India, it is around 4 million. And see, another thing here in India, actually, even many cases are not reported one. So that is also another problem. Even Parkinson disease, multiple sclerosis disease. So these are the different cases, and in India, still awareness is still at very nascent stage. Now, when we take about so seeing so many cases, see, now so it becomes very much essential to address these things at the earlier stage. So when we are saying basically the brain imaging techniques that can be basically divided into the four parts. So four basically, first is basically the magnetic resonance imaging, another is computed topography. When you are talking about computed topography, what we are saying basically that it is basically the X-ray. This is the X-ray basically at the brain level. But can you tell what is its basically disadvantage? It contains basically the unhealthy radiation. What about the thing, see, magnetic resonance imaging? See, magnetic resonance imaging, see, that we are talking about. So, but what is it? Here, see, these radiations disadvantage are removed. Why? Because we basically take the image actually. Image basically based upon the, see, again, that coupling, the dipole, etc., this magnetic part. But what is its disadvantage? What is the difference between fMRI and MRI? If you see, it's actually a bit expensive, right? And another part here, see, when you talk about the fMRI, it's actually sound. fMRI is exclusively for the brain regions, and a lot of sound is there actually when these type of machines are used, etc. So that actually creates a bit problem. Then another is positron emission tomography. In that, again, only the it is based upon the radiation. Well, good part is that it is able to find out the minute change, right? So when you talk about the this imaging planes, etc., here, so what we are saying that it is uh, coronal, it is front and the. So when we are taking, so three type of views are there basically. Coronal is there, that is basically along the head. Axial is basically along the area, so that is basically, and sagittal, right? So when we are taking basically the coronal front and back view, so there you can see easily see here. Axial is basically the horizontal view that is there, and sagittal is there, that is basically the lateral view. What are the challenges in the traditional diagnosis? When we say about we say the reliance on the manual analysis of medical images like MRI, CT is time intensive and prone to human error. Subtle, so that is subtle pattern in these images may not be visible to the human eye. The combination of neuroimage and ML not only enhances diagnostic accuracy but also reduces the time and cost of clinical workflow. So that's why see we are here. The time and cost has been actually very effectively reduced when you're taking about basically mass level. So that is there. It bridges the gap between vast medical data and actionable insights. So coming out of the motivation, see when you see basically the brain disease such as see brain tumor, Alzheimer and strokes are on the rise globally. When you say basically the traditional methods of visual analysis of medical images rely on the experience of radiologists and clinicians. What we are basically talking here is not only that they need to be dependent on the radiologist and clinician, that can we do it on the automatic basis. Then we come to the part neurological disease. So neurological disease often presents subtle signs that may be hard to detect in early stages. Access to the specialized healthcare resources is expert radiologist is limited here actually in certain regions, especially in you say tier 2 cities and tier 3 cities. Machine learning allows for the integration of patient-specific data to tailor personalized treatment plans. So thereafter, see then what do we say here? See, so access to so machine learning allows basically for integration of patient-specific data to tailor personalized treatment plan. What are the different steps basically for analyzing the neuroimage? When we talk here, see basically the different data collection methods are there in the form of publicly available data sets and other local data acquisition studies. Various pre-processing methods are there such as contrast enhancement, noise reduction, RGB to gray conversion, data augmentation and segmentation, etc. So now see the image part has basically begin. But if you realize it, see what is basically special in the MRI image, that which image you need to take. Whether you take the coronal view, whether you take the axial view, whether you are taking the sagittal view, right? So which one is the better one? So when we are saying, so what do we do here? Contrast enhancement. Are you able to recall? How did we do? Now it is coming the same basics. Contrast enhancement. How did we do? Are you able to recall histogram equalization, histogram extension? So there basically you used it. So even we will say noise reduction. Noise, basically to reduce the noise we use basically a different type of filter. RGB to gray conversion, that is the part here. Data augmentation and segmentation. See why we are doing it, so that the amount of the data, length of the data can be reduced and it can be well processed. Different categories of features using various feature extraction methods. So when we are saying basically the post-processing methods such as basically feature selection, feature sampling and dimensionality reduction technique. So post-selection, see, remember pre-processing, post-processing are a bit different. So here basically you select the feature because here your main focus is upon whatever feature that has been working can be reduced its size. So that is it. Feature sampling, dimensionality reduction technique, that is it. Result analysis method in the form of classification algorithm and statistical test. So that has been done. So in the basically feature extraction, feature selection, as now see you would be aware that in every image processing task that has to be done out. Only certain things you need to do here. What you need to do here? So you here basically create a subset of new features, right? By combination of existing features. So what is basically what you are doing here? See, for example, this n is there. Total n is there, and you are selecting out some of them where n is so basically capital N greater than 2m. So what we are saying, so we can select out the main feature. What is the difference between feature selection and feature extraction? If you see here, see that basically normally we basically carry out the feature selection after the feature extraction. So what we are saying here that it is here creating a subset of new features, right, by combination of the existing feature. And feature selection is basically that selecting a subset of relevant features to use in model construction. So here actually see the basically subset of new features are changed. Here the techniques has been applied during the feature extraction. But in feature selection actually instead of technique, whatever feature has been generated from that feature, we are able to carry out the information. Now the question arises, why do we need to do the feature selection? Apart from basically reducing the size, definitely irrelevant variables, noises are there, computer concept is there. It reduces the overfitting and increases generalization capacity of the model. So now see coming to basically the what the work has been already done in this part. So when we talk about basically the feature here, basically it is a gray level co-occurrence matrix. Gray level co-occurrence matrix here basically you are detecting the brain tumor. Then thereafter it is the mean standard deviation variance. So in that here also you are basically using brain stroke detection. And then you are using basically GLCM. Here you are using Alzheimer detection in GLCM. So if you recall, see, we have already done it gray level co-occurrence matrix. Are you able to recall? See, when did we did it? Day before yesterday. See, on the Saturday basically we covered that topic. Then gray level co-occurrence matrix and plus local binary pattern. It is basically used for the multi-graph brain tumor detection. Then we are using, we say, the graph Fourier transform, graph convolutional neural network. It is basically used for the autism spectrum disorder. Then we use basically the discrete wavelet transform. Discrete wavelet transform we are using basically pathological brain disease detection. Then you use basically the GN and GFT. Here you use basically the brain tumor detection and the Alzheimer detection. See, and another part basically when you are using feature extraction, when you are using textual based features, so what you are using the GLCM, we are using basically the gray level run length metric. So in textual basically what is done here the spatial relationships are captured between the pixel intensity. And the discrimination is improved between normal tissues, benign tumors and malignant tumors. And what is basically the disadvantage? See? Here, see the disadvantage is basically there that require predefined parameters to compute features. It is struggle with representing complex structure or irregular pattern. It operate on a single resolution and do not naturally account for hierarchical or multi-scale structures in the image. So this is the thing. And thereafter, see, we move toward the part basically the LVP. LVP again, see, you've done it. Local ternary pattern, histogram Fourier gradient, Gabor filter. All these basically focus on the local patterns and texture, gradient information and edges. It is rotational invariant. It suffers in capturing the global relationship. See, for example, the local level, etc., oriented Gabor filter, they are couldn't capture the global relationship, structural dependencies, and complex topological feature of the brain. So, are you able to recall? See this GLCN, gray level co-occurrence matrix. Now coming to basically the shape-based feature. In shape-based feature, see what we are saying that it is area, parameter, circularity, Zernike movement, U movement. These basically the basic geometric features are useful for analyzing the shape and size and shape of the lesions. That is invariant to the transformer. It is sensitive to noise and a small image distortion. They might not capture the more uh, complex, intricate feature of brain MRI images. So what is the key thing here that it doesn't effectively capture very fine details or highly irregular edges. So thereafter we also do the feature fusion. Feature fusion is basically you are using the two techniques that LVP plus EWP that is basically gradable and that GLC and that HOB plus GWF. What we are saying here, see that fusing multiple feature extraction leads to a large number of features, as we did it in our facial expression, and which increases the computational complexity and can lead to overfitting. So what we can do, see, we can combine LVP and Gabor filter. It allows the system to access both local texture information and frequency-based features. Also, the one thing that to capture fine scale texture and information, spatial age-based information and frequency-based features, um, GWF, GLCM, HGPP, and HUG are required. Then we will in the GLCM, the gray level co-occurrence matrix. What did we realize that it is combines texture with geometric shape information, where the deep learning models are used, which capture basically both low level and high level features. Combining these features can provide a much more detailed understanding of the image. So the thing here, the thing of the DWT, it is basically easier to compute. A series of low and high pass filters are used to study the image at different scale. DWT is the most commonly used feature extraction technique. So what is the advantage of this thing is basically choosing the correct set of Choosing the correct choice of wavelet is basically a tedious task. It is fine that it is giving basically low and high pass filter and commonly used, but it is not easy to find the choice of wavelet. It struggles with irregular or complex shapes like tumors, especially as non-uniform boundary or significant texture varies. So then it really becomes difficult to diagnose. So regarding the curve-light transform, see again it has used curve-light transform excels at capturing edges and curves, which provide basically multiple directional component at different scales, allowing the transform to represent edges in various directions. So what is the disadvantage? See, as you are saying that basically capture edges and devices, so it can still be computationally intensive. So we struggle with noisy images that have complex patterns. Replay transform. Replay transform basically can provide increased robustness to distortions, scaling, or transformations that might affect the image or signal. Replay transform to capture fine scale variations. They are particularly useful in texture analysis. Replay transform designed to provide a better representation. So it making them ideal for image data where pixel intensity values often change drastically. See, that is the beauty or the basically nature of the this signal. What is its basically disadvantage? The replay transform is effective in handling signal or image at different scale, but it can come to time expensive for high resolution. Particularly when high order transforms are used, replay transform to analyzing non-statistical but statistical with certain type of complex irregular data. So now coming to the part CP feature, then we go to the graph Fourier transform. In the graph Fourier transform, basically we, again as we discussed in the morning that we obtain from the graph vectors and then represent signal into vertex and graph spectral domain, and thereafter you find out a new insight, and definitely it can be easily checked out that whether it can be validated or not validated. Identifying the right graph structure, identifying the right frequency representation of the graph signals. So in spectral graph wavelet transform as you scaling functions extract information from the spectral decomposition of the graph. It is simpler. So when we are talking about the spectral graph wavelet transform, so here see actually you identify the right graph structure, identify the right filter. Here scaling functions extract information of the spectral decomposition of the graph Laplacian. It is simpler than the traditional wavelength. It offers better management of selection of wavelet scale. Graph convolutional neural network. It basically captures local relationships and can be extended to capture global dependencies through multiple layers. So that again based upon the graph signal processing. Unlike a traditional neural network that assumes regular data, GCN can handle irregular analysis of data like social network, citation network, or point cloud where the graph connectivity may be sparse or dynamic. It can be computationally impressive due to expensive due to need to aggregate information of the neighbors in each layer. So when we are saying basically training of the large graph, so here we are saying it can be computationally expensive due to the need of aggregate information from neighbors in each layer. The performance of a GCN heavily depends upon the graph structure and how well the graph represents the relationship in the data. So when we are saying basically here the performance of GCN, it heavily depends on graph structure. See, for example, either you are taking fundes or you are taking basically the functional, you are taking the correlation or you are taking the. So see, initially as I used basically two algorithm when I started with the facial, but in image it is not that easy task. So image what it is to be used to done. See, for example, when we do it, see KNN, it can be used to solve both classification radiation problem. It is very simple to understand and easy to implement and debug. So here basically you find out a hyperplane that best divides the data set into the two classes. So, thereafter then we find out basically the SVM. In SVM basically you find out the hyperplane that best divides the data set into the two classes. So in SVM basically allow the good generalization performances more than other linear classifier. So as even I used it here, but also here it proves that there is a high computation complexity to preserve the complex structure. What do you mean by PCA? PCA basically again the principal component access that used for density reduction, unsupervised learning algorithm. It reduce the dimension of your data without important loss of information. So for example, if data is linear, continuous or complicated, manifold PCA fails to process data. So then we are saying it is basically used for density reduction and classification supervised learning algorithm. So LD is a simple algorithm that does not require extensive hyperparameter tuning like more complex and algorithm. So there you can see that LD is the feature of each class are known and distributed, which is often not the case in real world data. So brain tumor detection, it automatically detects the important features without any human supervision. ANN can model. So ANN basically can model complex nonlinear relationship between inputs and output. Artificial neural network and require large amount of labeled data for effective training. And then we can also address basically the GCNN. GCNN against a graph convolutional network, it is a general version of CNN that can work on data with underlying non-regularized structure. Here basically you identify the right graph structure. GCNN, it includes basically the progression. So in GCNN, what we are doing here that we are using basically brain tumor detection, glioblastoma progression, and multiple type lower grade glioma classification. So GSN is a generalized version of CNN that can work on data with underlying non-regular structures. It basically identifies the right graph structure. So now coming to the part literature survey. So what has been done here? See, when we are seeing basically feature action, feature selection, they are important part based on variety of literature, graph signals, many different engineering science fields has been taken, GSP, enzyme detection, brain tumor detection, glioblastoma progression, and multiple layer low grade glioma classification. Majority of work performed in different type of disease detection, classification, emotion, sensor network, image and video sequences, and it is biological blocks. So whenever we are saying this literature survey, you need to check out that what are basically the areas which may be improved. So when we are saying here, so graphs, see GSP basically used here in this one, disease classification, sensor network, video sequences. So it has been introduced to extend the knowledge of classical signal processing to a regular domain by graph and enabling the analysis processing of data. So when we are what we are saying here that it has been introduced to extend knowledge of classical to irregular domains by graph enabling the analysis and processing of data that resides on structured yet non-Euclidean spaces such as social network, sensor network. Mentioned in the another paper, the graph matrix, it is not always clear when or why we should use the normalized graph Laplacian eigenvector, the unnormalized graph Laplacian eigenvector. The data clustering and feature reduction can also benefit from tools to develop under the GSP framework. So, for example, the graph Fourier transform may be used to reduce the features. So what we are saying, see, it is not when or why we should use normalized graph Laplacian as data clustering and feature reduction can also benefit from tools developed under the GSP framework. For example, graph Fourier transform have been used to reduce the features, see, as also we have seen in the facial expression recognition. Now see come to the part which is the methodology. So what we are going to do in the methodology basically we are doing with the deep learning, machine learning and the graph processing part. So this is what we are doing here, that neuroimaging we are taking here, the pre-processing is not necessary. Again we do the pre-processing, but thereafter we, so as we see, if we directly see basically the deep learning from the image, see here pre-processing is not necessary. Why it is not necessary? Because you automatically features are extracted, no more any techniques are there. But what is the disadvantage? The large amount of data, large bulk of data is there. For the machine learning, see pre-processing is there and exclusive feature extraction is there, which is either based upon texture, shape, statistical, and thereafter you do the feature selection and you do the classification using ML. And in the graph signal processing, see here actually the pre-processing is there, here graph construction is there, here your feature extraction is there, feature selection is there. So this is as we in the see in the first slide also we have seen it basically the 5 type of views are there. So here see it's just here due to brain tumor cases by it has been shown here. So again going to obviously motivational proposed work in deep learning taking large data set raises a cost and complexity of computing. But here see novel future fusion technique with boosting classifier has been proposed. Imbalanced data set and imbalanced data set, see what you can. So if imbalanced data set is there, then definitely is a problem. Then absence of explainability and transparency in the production of. So what is the issue of overfitting also comes there when your data is less. So here see when imbalanced data is there, so we can use basically a SMOT. SMOT is basically synthetic minority oversampling technique that is used to balance the majority class and the minority class. Safe basically shapely additive explanations that values are used to find out the importance. So to find the importance of feature and the finally see so see the question Parvesh has asked a question. So if I need to start with the initial for writing a research paper, can I start with 20-30 MRI images and apply image processing like feature extraction through various methods like text analysis and apply various best feature selection, correlation, comparing all to find the accuracy needed to good start to work on the medical image need better. Okay. See, you can see start with definitely you need to start with basically the initial some images, but when how you will validate the result. Validate means basically how you will compare your result with the other one on the normal benchmark. So there actually you may start with even you may put in the some conferences, but finally see when you are going to write it overall, then you may need it. But definitely you can start with it. That's a good idea. Absence of explainability and transparency in predictions by the model. So here see what we use, basically we use shapely additive explanation that values are used to find the importance of feature. So here the issue of overfitting is there. So here we use basically the linear discriminant with five-fold cross validation. When we are talking about see, methodology, so what we are saying is the brain MRI images are there, you do the pre-processing. So what we are doing in the pre-processing as we are see doing this is the resizing. Resizing also we did in case of the facial expression clay heap. What do you mean by the clay? Are you able to recall what is this term? So when you are seeing, see here the clay is there. So what is this? This is the clip level adaptive histogram equalization. Yes. Contrast, yes, it is basically. If you have seen it, that we in the beginning we discussed it. Then you use basically use RGB to gray, so that again see the three plane information come in one plane only. Then you use basically median filter. Median filter, are you able to recall see whether it is a linear or non-linear filter? Now it's all about the application of whatever things that we have started with. So median filter basically the type of the non-linear filter. So now it is block clustration. So HOG feature is there. HOG plus FOS. What is basically FOS? This is basically the first order. So the first order statistics, what we are saying here, so both we are basically using. So what is basically the HOG? HOG basically will take care of these local things, right? But FOS, etc., they take care of the global value. When we are saying, so both the things are completed the things. So now what we are saying that feature sampling is they are using a SMOT and feature sampling. First basically you have extracted and thereafter feature reduction, feature selection. That is basically using the LDA. What is LDA? That is basically the linear discriminant analysis. Even see we try to use basically the PCA, but PCA did not give that much result. So you can use either of them. So in classification basically you use basically the different type of these machine learning classifier, that gradient boost, that is extreme gradient boost, it is light GVM, that is cat boost, and then it is you are able to find out that it is a tumor or a non-tumor. So this is just see for conference actually yes validate. See in some conferences previously it is not necessary that in all the conferences, but in if it is there, then it is no, it is not important for all the conferences. Then you have to compare the result uh, within your paper only. That also it can be done initially. So now coming to the part feature extraction. In feature extraction, basically the histogram of oriented gradient and first order static techniques are used to capture both edge, texture, and statistical features. So what do we say here? That HOG captures edge and texture detail while SOS provide statistical insights into the pixel intensity distribution. Combination of these HOG and FOS features enhance the model's capacity to recognize and distinguish relevant features for accurate classification. So what we are saying is this is the edge and texture details. This is basically at the neighborhood level, and this is at the global level. All the so that has been incorporated. So what is basically the HOG? Again, in context of here, as it has been already, we have seen it earlier in the even facial expression and earlier in our basic lecture. It is a feature descriptor that captures the structure, shape, and gradient information in an image. So here, what are the key steps here? So key steps here are basically that it is compute basically the gradient magnitudes and orientations for the image. So what do we, gradient magnitude and orientation both have been taken. So how do we do it? We divide basically the image into cells and compute a histogram of gradient orientations, that how many orientations are for this one. We count it basically instead of the color pixel if we read that. In this part, you need to normalize the histograms across overlapping blocks to enhance the robustness to lighting and contrast variation. Then you will concatenate normalized histograms to form the final feature vector. So when you again see, when you take basically a block size of 1 by, as you take and see 1 by 1, when you take basically block size 2 by 2. So what we are seeing here, see there is a number of features, see that is there, that accuracy is very high, but as soon as you take the 2 blocks is basically, then the number of feature uh, has been also got up because we have increased the block size there. And here when with this one, so here it will decrease 64 by 128. So here it is 756 and here it is 93.2. So now we talk about basically the FOS, the first order statistics. And the first order statistics, what we are going to cover here, that it is the feature basically that it is minimum, maximum, this 2, this 3 here, this 4 here. So what we are saying is mean value etc can be calculated, median value that you can, minimum, maximum, so that is image. So from where you calculate, again see in your matrix you need to calculate this part. So KMN is related as the image pixel intensity, the total pixel is related as N. Now the see methodology, see what we are going to do in the smooth. See if you see these two diagrams, see what you are seeing. If you are seeing the diagram, this is one, and so what you are going to do in this feature sampling using a smart. Here see you what you see. If you see this C2 image, see here all the picture has been made clear. So for example, tumor image is there, non-tumor image is there. We need to balance them. We need to see when we need to train equally with tumor image and equally non-tumor image. So what do you going to do when non-tumor images are less? Then you'd use basically the smooth. What do you mean by the smooth? The smooth means basically synthetic minority. So what we are, so what has been said here that so both have been say made equal by using the smooth. So what is basically smooth? Smooth is synthetic minority oversampling technique. It is basically following the feature extraction in order to overcome this difficulty and improve the model's capacity to acquire more broadly applicable features. So by interpolating between pre-existing samples, we also generate the synthetic samples from minority class after a smooth, so that has been shown here. So now coming to the methodology, what we are doing in basically the LDA. As LDA, see, when we have basically extracted the feature, then its length can be reduced. So is saying this is basically the augmentation. Augmentation, yes, is smooth. Smooth basically we are actually balancing, because otherwise how can you train it? So yes, augmenting on the where the data is less. To reduce the feature set, see it entails basically projecting the initial feature space onto a fresh set of dimensions referred to as discriminants that have been specially designed for class distinction. The eigenvalue decomposition of the scatter matrices, which measure the variance within and between classes, is how this is accomplished. So, how do we decide? See again, see that eigenvalue decomposition of matrices, it is helps to measure the variance within and between classes. The optimal separation between the altered features is ensured by the LDA. It chooses the directions that optimize the proportion between within class and inter-class variation. So regarding the C result and the C discussion, when we see it, as we have again seen, when so what are the parameters that are going to play a role? See, so this is basically the accuracy, that is here the precision, the merit is higher, it is a recall, and that is basically the F1 square. So another thing, see this experiment using different feature extraction techniques. So here we only use basically the HOG, and in the trial 2 we use basically the FOS, and then we trial their combination with that feature vector. What are we saying? See, when we are saying trial 1, trial 2, trial 3, it means which feature vector you are used. Where you are used, that you can see here. See, here we are seeing after pre-processing, so we have used this feature. So we have used this feature, and thereafter we have classification. So here either HOG or both of them or either of them. So to reduce the feature set, see what do you see? We project the initial feature space onto a fresh order dimension and refer to discriminant that have been specially designed for class distinction. So that has been, we already covered through that, we have done through. So here it has been shown here, the trial 2, 3, see that has been shown. What is the key difference here, that when with LDA, when it has been used, so when it has been used with LDA, so you can see the accuracy here, that here it was basically 89.3, here it's a large reduction, it is about 9%, it is 7%, and in cache boot it is again wonderful increase. So what we can say is that that's how this basically this feature reduction really works here, and five-fold stratified cross validation is also used here. When we come to the results and discussion, so what we see that the ROC curve that has been shown here for all the classifiers, that gradients, see all it has been. It has been shown here to this one. So thereafter, then we also use basically the explanation. What is basically the SAP value? SAP value, see, if you recall, see, safely additive explanation. Safely additive explanation are used to find the importance of feature. So here, see, it has been shown here, see this feature, and thereafter it has been towards the C6 part. So it has been at both the values, it has been enlarged here. So here you can low to high, it is using the cat boost classifier, its value is shown. So here it is basically the final the comparative analysis. So here you can see the result when we are using both of the techniques, HOG plus FOS, the result is basically around the 98.3%. So what's the conclusion in this article? Novel feature fusion technique proposed for tumor detection for image enhancement. See, contrast, actually this contrast limited adaptive histogram equalization is applied with median filter used to reduce the noise. Features are extracted using HOG and FOS, and then you do using LDA. And then after, see, we have used five-fold cross validation that is implemented to address overfitting. Apart from it, we have used basically the LDA. So experimental indicate that the cat boost classifier outperforms the others, achieving an accuracy. This is a fairly reasonable, and an AUC of 1. So thereafter, so it is basically a two type of classification: tumor, non-tumor. We go to the multi-class classification. On the other hand, HOG and ROS fails to capture a spatial interrelationship, but that is the problem. In non-Euclidean data such as brain MRI, in order to get over this, we intend to explore into using graph signal processing technique to enhance performance of brain tumor detection. So here we just take a break. So we will meet thereafter. If you have any questions, you can come out or after the break. Just short break. So welcome back to in this our afternoon session of ninth day. Any question before moving further from this brain tumor identification using HUG and FOS? Okay, so no question. So see, now when we come up with the enhancing brain tumor, use future fusion. Now see, if you really see here that we have addressed the two problems. For example, like the deep learning, etc., we are not use the deep learning, we are able to use the machine learning and see such as a good result. That is, and our that work was basically, see as I told you that this is the work primarily done by my student research scholar Suman, that our work was basically published in the 7th International Conference of Signal Processing, Computing and Control. It has been published with enhancing brain tumor detection in MRI with future fusion and smart optimization technique. So what we are saying, see, and the problem, see, whenever see you are seeing any research, find out the problem. See, what is basically the problem and what solution can be suggested. So problems in deep learning, large data set raises the cost and complexity of computing. And see the major problem, if you really see with deep learning, see it requires see, additional GPU, etc. Additional, so which is not very commonly available in the our normal systems, normal computer systems. So conventionally techniques generally use single feature extraction techniques. So what we have done, we have basically proposed a novel feature fusion technique with gray level co-occurrence metrics and first order statistics. Imbalanced data set, where imbalanced data set was there we use basically SMOT. Imbalance means basically, for example, that there was 155 images, that is basically the tumor, and 98 only for the non-tumor. So we balanced it. So training wise, it's a balanced case for both of them. Less accuracy in ML classifiers. So when this is a problem, so how it was been addressed? So see, ML classifier, if you really go into the detail, there the different parameters are there, sub parameters are there. So we can tune those parameters, and how we can tune those parameters? So for that we have used the algorithms like grid search optimization has been used and gray wolf optimization that has been used in this paper. Are you recall the gray level co-occurrence matrix? Yes or no? If we let me see.
Desktop.
Just a minute, let me show you the gray level co-occurrence matrix.
शेयरिंग हो रहा है टाइम लगेगा.
See, are you able to see the gray level co-occurrence matrix? I think now are you with me? Yes, so see, this is the thing. See, the beautiful thing is there, see how these small fundamentals, small see, this thing has been really enhancing the our real research applications. So this is the thing. See, for example, this pair is there. For example, this is 0 to 1, this is 0 to 0. So what has been checked there that between 0 to 0, when it is 45 degrees, so it is 1, it is 2, it is 3, it is 4, it is 5, this is 6. So this is 6 pair that we have calculated. So this is gray level. Gray level means basically the pixel co-intensity. Co-occurrence means when they are in the neighbor. Neighbor, and also the important thing, it is basically the orientation is included. Why orientation see matter? Orientation actually matters see because it is not the normal neighborhood relationship that we are, because we are able to, we want to take into account the this orientation part. That's why. So for the different angles, it has been taken. 14 textual measures defined by Ehrlich. So it is the angular second movement, it contrast, correlation, variance, sum average, sum entropy, difference variance. So all these, see, these are part of the GLCM. See, angular second movement, see, that's how you calculate it. Again, you are able to calculate the contrast. It returns a measure of local intensity contrast. See how different pixels are. See here again you can see for the 0 degree, here you can see. This is all about that we discussed yesterday. So finally the meaning is that, see, now you have covered the sufficient basics. You only need to apply. You need to refer that material, that basic material. So now see methodological proposal, see what, see when we less accuracy in ML classifiers is there. So here see you can see what is basically against the different type of images are there, basically that is at the sagittal, axial, coronal. So here see first we do the image processing, we do the contrast enhancement, then this color stripping, that RGB to gray, noise reduction, and thereafter you basically GLCM, gray level co-occurrence matrix, that you use first order stochastic, then you use basically the feature fusion, then you use basically feature sampling. But along with it, see what do we do? Here we do the hyperparameter tuning. See, simply machine learning is not sufficient. We use it here so that the accuracy can be further increased. So what we call it, if you recall, see, so this is basically the nature inspired algorithm. What is this? This is basically the uh, gray wolf optimization, and this is basically the grid search optimization. That is the thing. Another other nature inspired algorithms are also there. Particle swarm optimization. I think you would have definitely heard about these things. So it would be clear that where do we use it. So any question regarding it, anything? So now see coming to the data set part. As we told that whenever you start any research etc., first you need to see the data set, because data set is the thing where you will be evaluated, where your algorithm will be evaluated. So here see we are basically what we are doing is a brain tumor detection. So it is basically from the Kaggle 253 data set. Kaggle 253, it comes by 253 brain MRI scan where tumor images are there of 155 and non-tumor images are 98. So scans are acquired using different imaging techniques such as, so see, remember fluid attenuated inversion recovery, T1 weighted 253. See, that's why we are saying, see, not for the deep learning, but for the machine learning that we are using. That's why machine learning makes it uh, is preferable here. And see, the another problem is that these are actually the tumor images, etc. Here you can't actually regenerate it. You can't take the different type of samples. These are the medical images. So that's why see when you work in the medical domain, many things, many constraints are there. So that's why see machine learning and our algorithms have worked very well here because it's limited data set. Deep learning is not likely to work here. So in pre-processing, see what is the pre-processing? So again, see as it means generally the visibility of fine details of biomedical images are low. See what you are seeing here, it's very difficult to see get it because all black and white and very almost a gray level it is there. So when we enhance this image, so that has been shown there. So thereafter, see what did we do here? See there we use basically a threshold image. Threshold basically you put up even threshold and it has been converted into the two part. That below threshold it is black and above threshold it is white. And what we have used here, are you aware? See, we have used this part. What operation? Which operation we have used? If you recall, see, it is basically the erosion. Erosion, that morphological operation that we have discussed. Are you able to recall? We discuss these things in under the morphological. Even see, we also use the ortho thresholding. If you see where is the ortho thresholding, just let me show you. This is the image segmentation and see what did we observe here. See, this is basically the hair. See what you are seeing. This is an auto threshold selection technique. It finds the best global threshold that separates the image into two classes, foreground and the background. It does not set randomly like Rubel threshold technique by maximum separation between the two classes, which are bimodal regions. The image is having two peaks in the histogram. So what we have done here, so this is the one here, and so this we have done. So, and another thing, see what we are saying. So, so are you able to see here? See, so here we see when we have applied it also thresholding. So our image has been divided into the two regions actually. One is the white, another is the black. And there actually see what we have done. See here we have this masking is there. So this is not actually the bit erosion. It is basically more or less like the it is set of operations, right? So it is even at the level it is even it is basically like the dilation, because in erosion actually see uh, what happens that white regions actually shrinks out, but it does not shrink out actually. So, but here see definitely the morphological is involved here, because once you have this set of threshold, then you have worked over it. Then the images are converted from RGB to grayscale, and 3 by 3 median filter is used for denoising. And thereafter see sculpt stripped images there, and so this is so here see what we are saying that in feature extraction. In feature extraction we have used the gray level Cochran matrix. Earlier we have used HOG and first order. See again remember it, you have to check out the different you have to check out the different basically feature extraction techniques, that which one is going to be more conducive to uh, find out the better, where you are getting the good accuracy. So you we need to have the clarity, and how you will get it, so sometimes from the literature review and sometimes see from the combination, because if new combination is proposed, then definitely something is new, then it is more likely to be accepted in the conference and the journal. So what about this GLCM and FOS? GLCM is gray level, so you calculate the spatial relationship between pixel intensities in an image. So assuring texture changes, 6 GLCM features are there. Here you capture the statistical information, meaning tumor intensity properties, FOS features. So both are basically complementary to each other. So gray level occurrence, here each element represents frequency at pixel with gray level adjacent to pixel. Adjacency here can be defined in terms of 0, 45, 90 degree, 135. For each pixel, you look at its neighbor in defined predirection, and this way you can calculate it. See, this pair is there, this pixel of interest is there. In gray level, so what we are see 6 parameters. See, even see in total it is 14 is there, but here see we have taken basically 6 one: contrast, dissimilarity, homogeneity, angular second movement, energy is there, correlation is there. In FOS, see these parameters are there. So see, whenever when you are taking basically these features, so it is not the one value, it is basically these, so it is basically set of values. So more the set of values, see more it is likely to give the comprehensive result. That's why. So It doesn't mean that you take only one parameter, you take all the parameters, and that is more likely to give the better result. Thereafter, we are using series of feature sampling here, see that we have used it. Then we come to the classification part. In classification, see, whenever you are going to basically train the data and supervised learning, you need to mention the ratio, that whether it is, this is how much you are going for the training, how much you are giving for the testing. So in this way, uh, even some people use it basically 70 to 30 also. So you need to uh, check out, see that which one is conducive. Otherwise, but normally we take it that 80-20 is a good one. So we can use either of the C classifiers here, whether it is decision tree, support vector, random forest, gradient boosting. But see, as we discussed it, that here in order to increase the C efficiency, what we are planning, that we are using basically these optimization techniques. How these optimization techniques is the parameters, the sub parameters which are part of the, which tune basically the classifier. There we use these optimization techniques to optimize it. So what is basically this grid search optimization? How does it look like? So here see what we see, that input parameters of models are there. So whatever your model, the grid search space construction, train the model with the specified parameters, and then you performance evaluation. Thereafter performance evaluation, you tried all parameter combination. If it is giving the good result, then it is fine. If it is not there, then you again train it. Then optimize the parameter for the model. Then you train again with those parameters. Then output is there, and then it flows. So whatever the gray bar. So here see again, see what is, and overall see they seems to be the same, but see what is their function, what is their in between function, how they are fit. So that is different one. So overall see what you can see here, that how the nature inspired algorithms are part of the our image processing applications. So this is basically the result and the discussion that you can see here, that effect of feature extraction and on accuracy. What did we observe? See, this was earlier 1.71 result, but when using this mode, see, remember when what we doing the synthetic minority oversampling technique that we are basically using. So when we are using basically smart, so now the supervised, under supervised learning, the accuracy has been gone up by 11%. That's basically a fair result. And what is the impact of the GSO? Grid search optimization, so that we have seen here. So grid search optimization, when we have used it, so what is the accuracy? It is accuracy has been basically uh, without a smooth. So it has been almost the same, but here see it has been increased here in the gradient boosting. And so this is basically the convergence curve, that how, so what does the convergence imply? So where, how it has lead to the uh, accuracy, where it has reached to the final solution, how much time it has been taken. This is basically the ROC curve is there. So when you compare it, basically the proposed approach with the existing approach, so here you can check out. So this is for the different type of data sets it is there. So this is another data set, BR35H. This is BREDS 2018. And so our proposed work, we basically applied it on the Kaggle 253. We applied this technique, and so our result was basically fairly enough. It is good enough. Remember, whenever it is basically about the medical image, so results are not that much high. So, in apart from it, it is good one. So what we say are that that novel feature fusion tech proposed for tumor detection or image enhancement, a contrast, glaze applied and median filters. That you have seen here. See how basically we use the uh, clay and median filter. Whatever we have read it, how it has become useful. So enhancing brain tumor detection, improving ensemble matching maximum voting. So what is traditional problems? See, so this has been shown here that traditionally method rely on single classifier. Here we would do propose ensemble learning method through a voting mechanism without the need for data augmentation. Even the data augmentation is smart, etc. If you don't want to use, we can skip it. So this is another alternative. So again, the brain MRI is there, pre-processing, feature extraction, classification, tumor, non-tumor segmentation. What is the key here? The feature extraction is need to be done at another level. So what is this one? Brain tumor detection BR35 as data set. What is the data set? Here see the things are a bit different. Here 300 brain MRI scan where tumor images are 1500 non-tumor. So no need to apply the SMOD. From where so it provides basically both T1 and T2 weighted images in JPEG format. This dataset was selected for its balanced class distribution, high volume and diversity of tumor characteristics, making it valuable for binary classification. Till the now, see, we have been going for the binary classification and performance generalization. So in pre-processing, see again the visibility of fine details of biomedical law. So again we apply the clip limited adaptive odds thresholding image cannot be grayscale and 3 by 3 median filter used for denoising. Gray level occurrence we have already read. It's the air feature extraction. Here see we have basically machine learning technique we have used. We can use either of the them. So but what we are saying here, a single classifier may not ensure higher accuracy. Right, this is the key thing. So what we are saying, ensemble learning, it is a combined learning, combine multiple classifier to boost prediction performance. So how? It is majority voting, vote weighting. So how? So and what do we use for the segmentation? Segmentation we use is a k-means algorithm. In k-means algorithm, so what we are saying here, see after the tumor images segmentation using k-means detection, k-means segmentation is an unsupervised ML algorithm proposed for tumor segmentation. Are you recall? See, K means we have already done it. K will use initialize randomly. Here the data together in K because some of the square distance data point centroid is left. K number of cluster centroid will be centroids are initialized. Each iteration Euclidean distance is calculated. It is assigned into respective clusters where the Euclidean distance is less. It continues, there is no change. Are you able to recall? See, we have done it K-means algorithm. I hope we have just done it. You may finding difficulty. So this is there. So this is basically clustering-based segmentation. So clustering is a method to divide a set of data into k-space number. It is one of popular methods. In K means collection data and k number group of data. So number of cluster k is there. So basically you take the centroid and distance object to centroid. So grouping basically based on minimum distance. So what we are saying it is. So we for how much part till we continue till the so how do we go across it? Begin with decision value of k number of cluster. Put any initial partition that the data. Take the first k training sample. Then assign each of the remaining training samples to the cluster nearest centroid. After each assignment, recompute the centroid. Take each sample in a sequence, and so this has been shown here. So this has been basically variable 1, 2. So if you recall, see that here we have taken this distance etc. here. So there we have taken this distance, and are you able to recall? See, we did it. Here we actually calculate the distance. Centroid 1 to 1 point. So this way this partition automatically comes out. I hope see you are with me. So this why the two clusters are obtained. Oh yes, thank you, Jyoti. So this is the thing. So this is basically K-mean segmentation. So here it is same thing is there. So category A is there, category B. And see, why are we interested? Because here also actually two uh, two sets of data are there, tumor and non-tumor. So that's why this is working well, this KB. Reason this is so very basic, this is there. So this is segmented image is there. So what has been done here? So here basically you have separated the image into two part here. One is basically this is tumor and this is the another the skull part. So this is what you can see when you use basically the what in ensemble you use basically the three machine classifiers. This is random forest, this is logical regression, this is DT, this is a decision tree. So here when we are showing it, so the accuracy has gone basically up to 89 level and this is maximum at the this one. So fairly it is yes in comparison to the random forest it is almost same. Yeah, what you can see here, so this is ensemble of this one. Conclusion here in novel ensemble learning machine with hard voting is proposed for tumor detection, for image enhancement, play, all things that we have already done it after. So this is basically a computational time and area under the curve is this one. After classification, tumor images are segmented using K-mean segmentation for tumor location. So this is basically the NS brain tumor identification using then graph Fourier transform. So what we are basically showing here, see again, see as for example, we discussed this, it can be represent that data into form of a graph signal. See, if it can be using the graph Fourier transform, then the question arises, how will we write the W? Because if we can write the W, then other part is simple. So can you think about it? Any guess? Any guess or any idea? See how we can plot the W here? See, recall, see how did we use it during our facial part, during a facial. And facial basically what did we do? We basically took the different pixels, right? We took the different pixels of the eye region and the lip region, mouth region. So what we can take here at the nodes. So remember, see, what do we need to take? Again, see, if you see again, this gray image is there. See, for example, whatever it is, this pre-processed image is there. See, there you can take at the grayscale values. Because see, even see one of the fundamental notion between taking the graph signal processing, that we believe that this region has some inherent relation. because it is all part of a one region. So definitely some relationship, some underlying relationship exists between these pixels. And when it lies between these pixels, then we are definitely begin to formulate or begin to design the W. How we can W? Again, see, if you do not know anything, you take the Gaussian one. So here we take the Gaussian one, and after taking the Gaussian one, then you are easily able to find out the W, and then after W you can find out the GFT, and then you are also applying the smooth. Why you are applying the smooth? Because we are using the same database, that is basically the Kaggle 235. And here we are using basically the ensemble classifier. We are using this one. So there, tumor, non-tumor. So this is shown here. So this has been shown, see how the basically this is applied, how the graph signal processing is applied here. So this is block diagram. Pre-processing basis. Here see this, as I told you, if you do not know anything, you can apply the Gaussian. So this is here, so this is using a smooth and classify you define tumor and non-tumor. So this is again the result, key result, original image. This is enhanced image, RGB to green, median blur, and you see what a beautiful it is. How much clarity with you can see in the final. It is tumor. It is easily visible. So accuracy, if you really call it, it is a Kaggle 253 when it is there. Trial one analysis without extracting any feature. If you do not see, because we can see the impact of it. Here is 83 CAD boost. See, some result give it very good. But when you take the GFT feature, when you take the GFT feature, so the result is earlier see in the this Kaggle 253, the highest basically it was 83. So Kaggle 253, it is 94 here. So, and then again with extracting the GLCM feature, this is a trial 2 analysis, GF feature, trial 3 analysis of both data set, binary weight. Even see what did we try, that we took the binary weight. Why was the binary weight? Binary weight, see if either the relation 1 or the 0. If they are in the neighborhood, then it is 1. If it is not there, then it is 0. That also be considered. With the binary weight, it is this one, and Gaussian weight, it is this one. So you see in binary weight, it is far larger. Trial analysis board data set. So here actually when you are using the GLCM feature. So this is the trial, another core analysis. So here this one. So what did it show? Can you interpret? What is the conclusion of this table 1, 2, 3, 4, 5? See, especially if you see when the result is low, then your interrelationship between these pixels play important role in identifying it correctly. So that's why this graph signal processing becomes very useful. If you recall, see in my facial expression, we mainly used it to reduce the reduce the dimension of the feature vector. But here we are using mainly to improve the accuracy. So that is why it has been shown here. So this is Kaggle 3 data set. This is here. So this is so what we have been used here. So this is basically the proposal that has been published in the journal. So this is such a good result. Both of them are good. This is a conclusion. New feature extraction approaches is there and random forest. So that GFT based feature improve classification of models that do not use GFT or boot data set to demonstrate model generalization and can robustness from data sources. So when two, that's why see I asked you whenever you are doing research, if two databases are there, it very firmly strengthens your testing result. So another C result, so basically there's the graph Laplacian based framework for classification. Even see we have done it for the Alzheimer disease, where the tissues are begin to deteriorate using structural MRI. So here see different, see here the different data set was there. What data set was there? Here basically samples from anonymous patients and 200 participants, each of whom has 32 slices of the image. It comprises four distinct classes: very mild demented, moderate demented, mild demented, and no demented. So this is the C images. And you remember, see, what is the really the most difficult part here? You see, can you guess what is the difficult part? If you see the image here, it's only the contrast wise, it is same type of shade. In gray, it is very, very difficult to find out. So even see our that work also has been basically published here. See, it is in the IEEE censor letter. This is the, and remember another change is there. What is the another change? Can you tell what is the change here? Change here, it is a multi-class classification. Earlier it was two only, tumor, non-tumor, but here it has four class classification. So here it has been shown, so that's why see it is, you see here that it is. So this is it. Other things are same or already we have done it. So this is done here. So this is again where we are using Gaussian weight here, and instead of using GFT, we are using a graphical wavelet transform. Graphical wavelet, spectral graph wavelet transform, far better results. So here see you can use it. So see this is basically the result. So that's how we conclude here that SAWT, here see it has been shown here that it outperforms conventional feature extraction method by effectively capturing the structure and spectral properties of brain tumor, leading to improved classification performance. And so here we conclude it, and here it's our team C. And see this work basically the brain tumor and Alzheimer work. This is primarily done by the Suman. She is doing here, and thank you for your patience for listening. Any questions? Any thing which you have in mind? Thank you definitely for continuing your um, constantly being there. Jyoti, you also deserve the full appreciation. I hope see these presents would help you in finding out a direction at your research, Sumitra. See whatever. So see what we have shown here. See initially we first show the basics and then we demonstrated how these things have been applied successfully. That can fetch you the research good results in the conferences in the journals. many people had been thinking about document, sign, etc. See, you can start with different type of fields, and if you really see, you have, it is different data set, but you apply the same means different type of techniques. But only you need to be confident, you need to vary the things, you need to vary the parameters, and you are going to get the result. Means that way image processing is really a very, very good field. Only you need to take interest in the way the your data set and the applying the technique. Gradually it will come. Thank you, Jyoti. It's really because see, once you easy see the way I have understood it, we always understand in that manner. And the purpose of this FDP is to convey everything in the simple way that things are easy. Only we need to take one step forward. So, thank you. So, tomorrow we will have the last session, and that will be taken by the Dr. Rakhi Sharma. She will take up the against the things in the medical images, how what she has done, so that we will see. And see, please, I request everyone to be there. That after 1 o'clock, that we will then have the valedictory session. Whatever your views are there, whatever your things are there, we will have the. I will really happy to see you there. You can switch on the camera, etc. You will all will be made the panelist, and it will be very good to see. So tomorrow we will conclude around at 1, and it will not take full time because we have already taken the session, evening session earlier, so that you are free to go at any place to enjoy the Christmas for the better preparation. Thank you all and wish you all the best wishes to find to do the best in your research.